All right. Hello, good afternoon, everybody. It's really nice to see you all here. I know some classes are still going in some studios, so hopefully others will follow up in the next few minutes. Thank you for joining us for today's event. It is really a pleasure to welcome Skylar Tibbits today to AUD. Before we begin, I would like to acknowledge that as a land-grant institution, the Department of Architecture and Urban Design at UCLA recognizes our presence, the traditional, ancestral, and unceded territory of the Gabrielino Tongva peoples. Was I supposed to do this? Guys, that's okay. Skylar is an architect, designer, and computer scientist. He has a professional degree in architecture and a minor in experimental computation from Philadelphia University, and a master's in design computation and master's in computer science from MIT. I usually don't read the degrees that people have when they come to talk, but I think the type of interdisciplinarity that Skylar brings to the table and that knowledge, I remember when I first met Sky, I was just like, what did you study? Like, what do you know? And how did you get to learn all of this? So I think Skylar is a paramount example of what interdisciplinarity can produce. His research focuses on developing self-assembly and programmable matters within the built environment as a focus. He's the founder and co-director of the Self-Assembly Lab at MIT, an associate professor of design research in the Department of Architecture, where apart from teaching, he serves as the director of the undergraduate design programs. Before joining MIT, Skylar worked at a number of design offices, including Zaha Hadid Architects, that's where we met, Asymptote Architecture, and Point B Design. He has designed and built large-scale installations and exhibited in galleries around the world, including the MoMA, the Pompidou Center in Paris, the Philadelphia Museum of Art, the Cooper Hewitt Smithsonian Design Museum, the Victoria and Albert Museum in London, and many others. He is the author of Things Fall Together, a guide for the new materials revolution, published by Princeton University Press in 2021, Self-Assembly Lab, Experiments in Programming Matter, published by Routledge in 2016, and Active Matter, MIT Press, 2017, and he's the co-editor of Being Material, also published by MIT Press in 2019. And he serves as the editor-in-chief of the journal 3D Printing and Additive Manufacturing. Skylar has received several prestigious awards, including the MIT Technology Review Innovators Under 35 Award, which recognizes young innovators whose work has a profound impact on society, the LinkedIn's Next Wave Award for Top Professionals Under 35, R&D Innovation of the Year, National Geographic Emerging Explorer, an inaugural Wired Fellowship, the Architectural League Prize Award, the Ars Electronica Next Ideas Awards, the TED Senior Fellow 2012, and in 2008, he was named a revolutionary mind by Seed Magazine. You get a sense from this list that apart from the usual suspects that we name, like the Architectural League and the institutions that recognize and propel architectural ideas, that Skylar is talking to a much broader audience that includes both incredibly specialized knowledge, architectural knowledge on the other hand, in the ways in which these two or many audiences can actually interact and talk to one another. He has been featured in numerous media outlets, in the usual architectural channels, and in other media that include Wired, the New York Times, and a TED Talk that has been viewed over 300,000 times. Through his teachings, Skylar challenges students to think critically about the relationship between materials, design, and the environment. His approach encourages interdisciplinary collaboration, fostering a new generation of thinkers who can navigate the complexities of modern design challenges. I loved this passage from the lab's website. I think that's where I pulled this from. It said, our sweet spot is the blending of basic and applied cross-disciplinary research that is often too costly, too risky, or too far out for traditional R&D. These ideas and projects of the lab are revolutionizing various fields, from architecture to robotics, and offer new paradigms in how we design and construct our built environments. And I think that while many companies of technology have R&D departments, the fact that this is happening from the heart of a tier 1 research academic institution and in connection to an architectural program is quite essential in terms of what it brings to the field and what the field brings back through that channel. Existing and previous partners of the lab include Google, BMW, Steelcase, Ministry of Supply, P&G, Converse, Airbus, Autodesk, and many others that demonstrate what interdisciplinarity can bring to architecture and what innovative architectural thinking can contribute to other fields through the exercises of connecting visionary ideas with practical applications. From self-organization to active textiles, Skylar embodies the spirit of innovation and technical prowess that defines MIT. His work not only enhances our understanding of materials and their potential, but also inspires us to reimagine the possibilities of architecture and the design for the future. Please join me by welcoming Skylar Tibbits to the evening.
Thanks so much. Thank you for the invitation and an introduction. I was just saying that I feel like I'm a West Coast person stuck on the East Coast. Every time I'm out here, it feels like home. So it's it's wonderful to be here. So I have a couple different roles. The slide that we're conveniently on is a journal that I run called the 3D Printing Additive Manufacturing Journal. And I think it's interesting because it crosses all different disciplines. So it's not just architects and designers, but it's mechanical engineers and computer scientists and material scientists and physicists, anyone interested in additive. And when I joined, I added the plus sign because I was interested in expanding it beyond just 3D printing. Like, what are other forms of additive manufacturing? Like, we have biomaterials and knitting and inflatables and all sorts of additive technologies. And then also because I wanted to hint that it's beyond just our vision of today's 3D printing and additive manufacturing, that really we want to push to imagine different technologies in the future. Academically, I run our design minor, design major program, and I'm really passionate about that. 2016, we started the design minor, and that quickly boomed to the second or third most popular minor across campus. It stayed within the top 5. And that's interesting because MIT is not historically known for design. And at that time, we didn't have any design program. We had an architecture program, and we had urban studies and planning, and we had media lab, but we didn't actually have design. And all of these undergrads wanted to take design because they were interested in infusing that with other disciplines and degrees. And so we have many minors that are design minors, but they'll be majors in biology, or so design in physics, or design in math, and design in computing, or design in you name it. And so we're interested in sort of educating and creating the future of polymath designers. And they might create new disciplines of design, or they might take design to other disciplines. So I teach in that, and I'm really passionate about that. And that program is part of this new larger program called the Morningside Academy for Design, and we're getting a new building soon. And so design has really started to become like a central focus on campus. And that minor major program is the academic portion of that. But what I'm going to talk most about is the lab. It's called the Self-Assembly Lab. We've had many researchers with lots of different backgrounds, different disciplines. It's everything from undergrads to masters, PhDs, full-time research scientists. Most of them have some design background, but especially on the undergrad side, it could be anything from brain and cognitive to computer science to material science. And we focus on these 3 scales, so materials, fabrication, and construction. And the ethos really is, how do we build smarter things, and how do we build in a smarter way, but by focusing on materials and their environment. Because it's not about adding more devices or more complexity. We're trying to find elegant ways to embed intelligence, information, agency, sensing, actuation, and really it's the intersection of materials and their environments. But when you make materials, you need to think about how do you make them. And so that's why we get into fabrication, and then how do we apply these at the larger scale. But when I was thinking about how do we start, one obvious place is, what do you imagine when you think about the future of construction or the future of almost any discipline? Most people will say automation. And similarly, if you think about the future of smart products, whether that's smart homes or smart cars or smart shoes or smart clothing, most people will think of devices. And we're trying to counter that. We're trying to say that it doesn't necessarily need to be about more and more robots. It doesn't necessarily need to be more and more devices. It can be more about materials. But how I got into this was really the introduction of computing. And I was interested in like the history of computing. This is Sutherland's Sketchpad, the first CAD tool developed at MIT. I think it was the 50s. And this obviously led to all sorts of computational tools, whether that's simulation or analysis or now generative tools. Computation has boomed in design, but it's boomed in almost every other discipline. And there's a parallel here to fabrication. This is the first CNC machine, 1955, developed at MIT, that then led to everything from printing to robotics, CNC machines, water jets, laser cutters, you know, the whole suite of digital fabrication that has boomed in our field and boomed in almost every other field. So in that way, we see how code became a language for design and code became a language for making things, for fabricating. But it wasn't really a language for construction. And we did this project for the 150th anniversary of MIT, and that became like very, very clear. That was a sort of big turning point in my career where we were making this installation, you know, looks like a generative installation that many of us has seen before. Lots of mass customization and unique parts and thousands or millions of bolts and rivets, blood, sweat, and tears, lots of hours assembling this thing. And most of the time, no one wants to talk about the assembly part. We just like magically show the final images, and we don't talk about how many students worked on it and how many hours it was, and you know, all these things. And I became interested in that part because before that, I was writing all this code and I was generating geometries, and then I was sending that to machines and they were fabricating, and there's like all this elegance in the process. But then the moment you go to assemble it, it's just brute force. You know, all of that information goes out the window, and it's just like slam this thing together, spend as much time and effort, you know, all of that complexity comes back. And most people drink the Kool-Aid of mass customization. And we think about like the more parts, the better. You know, it's free complexity in 3D printing. But that's not really the case when you have lots and lots of parts, because those lots and lots of parts have to come together somehow. And so I became focused in on that. Like, what would code for construction mean? Like, what would it mean to think about it through the lens of assembly? And at that time, when I was a grad student at MIT, I was working with Neil Gershenfeld's the Center for Bits and Atoms. And we had a programmable matter grant at that time. It was under DARPA and it was called Programmable Matter. And so I was working on these robots, and they had them down from the millimeter scale all the way up to like meter scale objects, and they would squirm around and reconfigure. And there was really small ones, and I was working on the larger ones. And they were kind of these like clumsy reconfigurable robots. And that's more than a decade ago. And at that time, programmable matter meant robots. Like if we could just make everything out of robots, then we could program matter. We could program the world. And I just remember sitting there, you know, trying to build this thing, and sort of side story, but there's like a 16-year-old doing his PhD working on this. Like it's really crazy situation. This thing cost like thousands and thousands of dollars. Now it's like a coffee table in my house, and you know, the most expensive DARPA coffee table. And I just became like really frustrated that like that's programmable matter. That's what we mean, is like this clumsy, complicated device with, you know, tons of parts and mechanisms and motors and stuff. And coming from the architecture world, I was like, that's just not going to work. Like we've seen many examples of just putting more robots in buildings, and like that's really not going to work. You don't want every brick to be a building. It's going to be super expensive, super energy intensive, hard to assemble. It's going to fail too often. Like that can't be programmable matter. So that was like the turning point. And I started thinking about assembly, and I started thinking about it can't be robots, and started focusing on materials. That the way to do this would be if we could embed more agency in materials. I mean, after all of us are materials. None of us are made out of robots, and all of us have intelligence. All of us have building blocks from the smallest scale to the largest of scales that communicate with each other and communicate with their environment and evolve and mutate and grow. So we should be able to do this with materials. So that became a main focus of the lab. There's kind of three main topics. And the first one that I'll talk about is programmable materials. The idea that we take physical materials, we program them to change shape, to change property, act as sensors or actuators. It's basically like turn everything into a smart material. And the way that we do that is we look at the material properties. We link those properties up with some kind of activation energy. So wood might swell with moisture, or temperature might activate metals or polymers. You'll have different activation energies for different materials, but the geometry is really important. So we use different forms of fabrication to manipulate those materials. So you can print it, you can mill it, you can weave it, you can knit it, and the geometry then influences the behavior afterwards. So you get some kind of transformation like folding, curling, stretching, shrinking. And so by linking up the materials with geometry, some activation energy, you get that programmability. And the way this started in 2011, 2012, strange story. I was at a coffee shop, and there was a person in line that had Stratasys shirt on. And I was like, Stratasys, like 3D printer Stratasys? And then we started talking, and I was thinking about all these robots, and I just asked, like, couldn't we print a robot? Like, couldn't we just print something that would walk off the machine? Isn't there a way that we could do that? We could embed all those properties in it. And that led to this project. They connected me with their material science group. And they had this weird material that they couldn't sell. They didn't know what to do with, and it swelled a bunch. It was like not useful for their typical printer. And they said, maybe we could use that. And so that material is a hydrogel, and it's at the joints. So that clear material at the joints, and it swelled when it got wet. And so we printed that material at the joint, and depending on how much you printed or what the geometry was, you would get different kinds of transformations. So we printed all these structures, like a line that when we dipped it underwater went to a cube, or a line that went into the letters MIT, or a surface that folded into an octahedron, or a flat sheet, like a record that did curved crease origami. And each one of these was a different mechanism, like a fold to 90 degrees, or a fold to an arbitrary angle, or a curl, or a twist. Or this one is expansion and contraction, like stretching. We did a 50-foot protein that folded underwater in an Olympic swimming pool. So all of these were different mechanisms that would do some kind of geometric transformation. They were at different scales. We were testing what would be possible with this material, but it was fairly abstract. And then I presented that. And a lot of people started coming to us and saying, like, could we do this with another material, or could we do it for this application? Could we do it with a different fabrication process? And that has led to more than a decade's worth of research on different materials, different collaborations, industry partnerships, academic partnerships, all with the same goal. Like, could we program other materials? So this is wood that morphs with moisture, and this is carbon fiber that transforms with temperature, get folding or curling. These are films that open and close based on low temperature or sunlight. This is a shading system we've been developing with Google. They're like stickers for buildings that open and close with sunlight. So we've done a lot of different materials, a lot of different activation energies, different kinds of applications. This one's auxetics. So these are like 2D or 3D structures that morph, they expand or contract uniformly. And that then started to get us into textiles. So we started slitting these and putting them on the arm. And then we started realizing, well, we could do it with actual textiles. This one was morphing based on moisture, and the pink is pH sensing. And so now about half of our work in the lab is textiles. Like out of nowhere, all the 4D printing stuff and programmable materials basically turned into a textile lab, and it's like growing sort of out of control at the moment. We have so many different textile projects. And the reason we got into this is because in textiles, you can take fibers and yarns, which is the material property I was talking about. You have the geometry, which is the knitting process. We can have macro scale and micro scale architectures of that fibers and yarns, so we can get different behaviors, and then we can activate them with different activations. And we can also have zones across a garment or across whatever the piece you're trying to make. It became 3 applications. The first one is tailoring, which is what you're seeing here. So that's basically, how do we take a textile and morph it to create a custom fit or a custom style? This is one we did with Ministry of Supply in their store. We made 20 dresses. They're all exactly the same. The robot activates the dress, and you can get different styles or different shapes. And the reason to do that is, one, for customization. As I was saying before, everyone wants mass customization. It's possible in printing or milling or machining, but it's not totally possible in knitting today. There's a lot of reasons for that, but one of them is knitting is dimensionless, so there's no units when you send a file. Another one is that the programming is super, super hard. And then there's a whole inventory issue of, like, if you make a custom XYZ in a factory, how do you get to the customer? So it's really hard to do that. So instead, what we're doing is we do a single SKU. So we do one product, and then we morph it so you can get custom. The second application is reversible transformation, like you saw in some of those videos. So we had to develop a custom fiber for that, and it reversibly morphs. Most of this is for like climate adaptation, temperature regulation, moisture management. We did a project with Arc'teryx on adaptive insulation, for example. So textiles that morph reversibly. Here's where you see some of that architecture. So we have these different materials. In knitting, you can change the material property stitch by stitch. So every single stitch can be a different material. And you can have these different geometries that allow it to morph, to expand, contract, shrink, have porosity, have thickness change. And so it's very much like a printer in that sense. Like, instead of droplet by droplet, we change it stitch by stitch, but it's totally scalable because every factory in the world, every textile factory has these same machines. So there's a really interesting connection to scalability, which printing, has its challenges. So here's like zones. So each one of those zones could have like different architectures that have those different behaviors. So you can have venting and cooling wherever you need it. And so you can get these kind of porosity changes, or you can get venting and flaps. So we have a lot of control all the way down from the fiber and yarn. I mean, theoretically, you can even go smaller, but we kind of stop at the fiber yarn production. We twist our own yarns. In the twisting process, we can combine different materials, or we can change the rotation of the yarn twisting to get different behaviors. And then we program the different architecture of the knit at this level or at the zone level. But then a third category emerged, which is about embedding functional systems into textiles. This is a spacesuit project that we did with Dava Newman, who's now the head of the Media Lab, used to be a director at NASA. And her whole research is on spacesuits. In spacesuits, we all know the like big, bulky, cumbersome ones that you saw in those videos, and they still use that today, and they're pressurized suits. And it's like the Michelin Man. So it's like hard to move around, it's hard to get in, and it's super vulnerable because if you pop it, you puncture it, you basically die. So there's a whole nother type that Dava's research and others have looked into, which is called mechanical counter pressure suits. And that's like wearing 20 pairs of yoga pants at the same time, like tons and tons of compression. You wouldn't be able to survive on Earth, but in the vacuum of space, it can protect you. The hard part, though, is that if you, like, let's say you take your arm, you need to get exactly the right amount of compression, even though your arm is a different shape and your arm's moving. So how would you do that with a standard cut and sew textile? It's really, really hard to make that. But with knitting, we can 3D scan the body, and then we can create exactly a uniform compression in a non-uniform shape. But we can also embed all these different functions. So the outside can be radiation shielding, the inside can be sensors, you can have like compression zones. We had this whole donning and doffing thing, which is a whole nother story because it's really hard to get spacesuits on, and how do you get the amount of compression that you need? So we had to develop this closure mechanism. But anyway, you can embed all these functions. Some of them are really rigid, like you hit them and they like sound really stiff and they feel really stiff. Some of them are super soft and cushiony, so it's comfortable next to your skin. Some are stretchy. And so that opened up a whole nother category of research that's just about these multifunctional fabrics. And we just did last week, I was here with a collaboration with Emico, the furniture company, where we tested this on furniture upholstery. So upholstery, just like many other industries, there's a whole problem of foam. Foam is really nasty, PU foams. You have to use glue, you have to use cut and sew, which has a lot of waste. There's a lot of labor and assembly. So instead, what we were proposing is that we could make all of the soft seating in upholstery by just using the 3D knit structure. And it's a single material. It's a monomaterial nylon. When we put it in the oven, it bulks up. So you can create the foam basically without any foam. And you still only have one material. There's no glue, there's no waste. It's fully knit as one piece. So there's no cut and sew. And then it can behave the same way as like a normal upholstery cushion. You can easily put it on, you can swap it on and off. It's sort of like fashion for furniture in a way. So we did this exhibition where we made a bunch of different covers for their like classic Emico stool. They can have different structures, different amounts of the like foam cushion, even though there's no foam. You can have different patterns, different aesthetics. They have different connection details. And each one of these is fully knit. So there's no like post-processing, sewing, or adding any components. They just come directly off the machine. In this case, we put them in the oven to bulk them up. And then we made a bunch of different experiments and showed that how you could replace the foam. But this same thing could be applied to car seats, or it could be applied to like foam in our shoes or packaging or many other things. So that's a more recent one. Anyway, there's more work in that space, but all of it is looking at how we activate materials to transform, change property, change behavior, change aesthetics. How do our materials do more for us, and how can we link those up with fabrication systems? The last part of that work was all on knitting, but we've developed two of our own fabrication systems. One of them is called rapid liquid printing. So in this project, we introduced this tank of gel. So we print inside of a tank of gel. The gel eliminates gravity, so we can print in 3D without any effect of gravity. That has a few advantages. One of them is we can print in 3D like calligraphy, so spatial printing. We can change speed or pressure, and that changes the line weight of the object. And then we also don't have to print layer by layer. So we don't have to print any supports. We don't have to print layer by layer. We can print really fast. And we can print very soft, stretchy materials, so like inflatables. So they can stretch up to 1,000% elongation, make soft robotic, like linear actuators, or these different morphable structures. And this specific one is a project we did with BMW on the future of the car interior. We were looking at cushions for cars, again, trying to replace foam. But in this case, could we embed all these other functions? Like what if the cushion could morph to create a perfect shape, or morph to change stiffness around your body, or be crash protection or massage features? You know, like all the functionality that's in a car seat now, could we embed that into one quote unquote like material system, like a macro scale material, that it could have all these different functions? And so this whole thing was printed with that process. And then we spun that technology out there in Boston. We've done everything from like home goods and lamps to footwear, prosthetics, medical devices. But the three main advantages basically is speed. So we can print very fast. Usually it's under an hour, so tens of minutes. Scale, we've done up to 4 foot by 8 foot. Normally it's usually like tens of centimeters, but really you can print as big of a tank of gel as you can make. So you just fill up a tank with water, and then if you have a CNC machine, you could print. And then we do very soft materials. So that's like the other advantage. Most printing processes use rigid materials. But in the lab, after we spun that out, we started focusing on high temperature materials, because that was one of the limitations. We couldn't print with anything that would boil the water. So here we print inside of a powder. The powder is basically very fine glass beads, and we print with aluminum, so molten aluminum, 600 to 700 Celsius, and we draw very, very fast. So under a minute, usually in 2 foot by 4 foot bed, we can print these aluminum parts, and then it's almost instantly cooled. So it's coming out of that nozzle, it's really, really hot, it's cooling very fast. And then we're just drawing in sand. So it's sort of like 3D sand casting, but we don't need any molds or tooling. We print with the molten aluminum. We can take it out, and then we can melt it back down. So you can recycle it, print and melt, print, melt, print, melt over and over and over again. It's much faster than the liquid printing, and it's, you know, orders of magnitude faster than any other printing, especially metal printing, which tends to be fairly slow. And it's very big. We have 2 foot by 4 foot, but you could be bigger, and then it's fully recyclable. One of our researchers, Zane, he's now at ETH doing his PhD, but he did his master's on this, and with Emeco, the furniture company, developed these chair and table prototypes. So each leg, so chair would be 2 minutes, for example. Each one would be under a minute, so maybe it's like 45 seconds to print those. And table, same thing. Each one of these, this whole table will be like under 3 minutes. Obviously the top wasn't printed, but these legs were done very fast. But one thing you'll notice is that it's kind of has this weird aesthetic, and that's because we're trading off resolution for speed and scale. So we're printing, you know, meter scale parts in under a minute, but you can get the precision by machining it. So you can do surface machining and then get whatever surface finish you want, or you can, you know, bore it, you could have threads in it, or whatever details and precision you need, you could post machine it. And the main advantage here over traditional metal printing tends to be fairly small, or even if it's large, it's very, very slow. And they're for high value, high precision parts. And we're sort of going the opposite end of the spectrum, like large scale, low resolution parts that we need to do affordably. So think of all the chairs or all the architectural components around us. We need to be able to produce them fairly fast. A kind of separate world that we've gotten into, in a strange way, is this world of granular materials. And there's 2 different versions of that. The first one is a project that we did with Adidas that is all on granular convection. So there's this phenomenon called the Brazil nut effect, where when you have a box of cereal or a box of nuts, the more you shake it, the more they separate, which is sort of counterintuitive, because normally you would like shake something and that would mix them. But when you have particles of different sizes, and there's some other factors like density and friction coefficient and stuff, but mostly it's driven by size. When you have particles of different size, the more you shake it, the more they separate. And so we started using that, and we made this proposal where you'd have a midsole. Everyone's midsole would be the same, but as you walk on it, then it would start to differentiate. So we had this midsole, we have a robot, we did 20,000 heel toe strikes, which is like the length of a marathon, supposedly. I don't run marathons, but that's what they tell us. And you basically can see the soft particles rise where you have the heel toe strike, and then the stiff particles drop to the bottom where you have the outsole. So that way you could have customized midsoles without having custom production. So you just fill these all with the beads. They have 3 different stiffnesses and 3 different particle sizes. You just start wearing it, and over time your midsole becomes tuned to what you need versus someone else. So that's a phenomenon called granular convection. The opposite end is granular jamming. So granular jamming is where particles get stuck. And the normal way you'll see this is like a bladder filled with particles, and you pull a vacuum on it, and then the particles jam. They act like a solid, but when there's air between them, then they act like a liquid. And it's really cool because it's reversible. So normally, you'd need temperature change or chemical change to have this kind of state change. But here you just have air flow between them. And you've also seen this when you go to the beach and you jump on the sand and it's really hard. That's granular jamming. The particles act like a solid when there's impact, but then when you play with the sand, it's really soft. So that's a state change because of the impact. The particles have nowhere to go and they act like a solid. We've done a bunch of projects on this. One was like an acoustics project with Google where we had these particles that they would make like acoustic panels. But the more interesting one is a project we did with Gramazio Kohler a number of years ago called Rock Print. And the weird backstory here is there was a jamming conference. I got invited to this conference called a jamming conference. And I was like, what do you mean by jamming? I didn't know anything about jamming. I thought there was like jamming out to music. Like, what do you mean by jamming? And it was all these physicists and material scientists talking about jamming. And there was like mining companies talking about jamming. There was like a Skittles manufacturer talking about candy. It was really weird, but they asked Gramazio Kohler, myself, and a few other architects to join this conference. And we had not done anything on jamming at the time. We didn't even know what it was. And I remember just sitting there and we were like, we got to do something with this. What can we do with jamming? And at that time, then we applied for a grant through MIT. It was an international collaboration grant. And our main goal was figure out a way to do jamming in architecture, but it can't have a bladder. It can't have a vacuum. Because if you have a bladder, like if your building is a bladder, you can just pop it. And if you have a vacuum, it's going to be really energy intensive. So like, how could we do jamming? And I went over there for a month and we just went to the hardware store. We just bought a bunch of stuff and we just tried jamming things. And like nothing was working. And then we finally found chandelier and screws. Those were the 2 things that jammed. And we were like, why does that work? And then we replaced this chandelier with string, and then it still worked. And we replaced the screws with rocks, and it still worked. And I was like, okay, that's it. Now we know how to do it. And then we've done now. We're still working on this. It's been like a decade, and we're still working on different. And they had 3 different PhDs do work on this, and lots of collaborations on like why this works. But it was a weird story of how we figured out how to do this. We did an early exhibition at Chicago Architecture Biennial. We had a yellow bounding box, the robot spitting out string and layering rocks. So rock, string, rock, string, rock, string, over and over and over again. And when you remove the bounding box, only the rocks that have string jam. Wherever there's no string, the rocks fall away. And it becomes load bearing. So we put 3 tons on top of this before we shipped it here. There's a whole nother Swiss story, which is funny, that they built this multiple times in Switzerland and loaded it until it failed. And then they shipped the rocks from Switzerland because at that time, we didn't know anything about it. We were just like, I don't want to mess anything up. Like, it works with these rocks. We're bringing the Swiss rocks. So we shipped the rocks over and the string. We built the thing. It worked. And at the end of the exhibition, we wind it up. And wherever the string is, it winds and everything falls away. So you're left with a pile of rocks and a spool of string. It's totally reversible. There's no waste. And we became interested in this because it's like reversible concrete. So everything goes from liquid to solid, but there's no 30-day cure time. So it's instantly solid, and then it's totally reversible. So it's a really interesting like solid liquid experiment. We did a project with Google on a landscaping application, but we didn't want to do this like all or nothing application. So in the yellow bounding box, like, a couple times before we got there, we tried it and it just didn't work. Like, you remove the bounding box after hours of work and then it falls apart. So, it was also in the early days where we didn't really know all the parameters. So in this case, we did a slip cast mold. So basically we move the mold as we go. You pour one part, then you can move the mold, pour another part, move the mold, pour another part. And we could make this. The other big advantage here was that we didn't have robotic placement. We just poured in chopped coconut husks. So we also went to Home Depot and found the rocks this time. We didn't have to ship them from Switzerland. And we were, the big division here was that the Swiss got a big Swiss federal grant. They had 3 PhDs working on this. We didn't have that. The US government wasn't supporting us at that time. And so Google was funding it. and we decided that we would go in like construction space. Like what's the fastest, cheapest way you can do jamming? And then they started focusing on more automation. Like how could you do more with robotics? So we started this one, and then we've expanded that. Now it went to a DARPA project and an Air Force project. And then we were doing runways and roads and all sorts of like construction applications, but all of it is about reversibility. So that's like the granular space and starts to get us to larger scale. But the name of the lab, self-assembly, became kind of the focus because I was really interested in that assembly process that I was talking about in the very beginning. Like, could we embed more agency in our parts so that they could help us assemble larger structures? And self-assembly is about disordered parts that build ordered structures. So all of us are self-assembled. Almost everything in the natural world is self-assembled. It goes from the smallest scales. If you talk to like biologists, chemists, material science, it'll be like nano to micro scales. But if you talk about geology, planetary scales, weather scales, it goes all the way up, like the largest of scales. Like no one's 3D printing a planet. Planets are formed through this process as well. We've done a lot of experiments over the years. The first one that we did was this flask where you shake it hard and the parts break, but you shake it a little bit softer and then they come back together. And that was like the first aha moment that this could work. We were working with a molecular biologist at Scripps, Arthur Olson, and this was based on the polio virus, and we did the tobacco plant virus and all these other like capsids. Then we started doing underwater structures. This one is a bunch of parts. Every part is unique in this case, and it comes together to make the chair. And then we did weather balloons filled with helium and Velcro nodes, and they self-assembled into these cubic lattices. And we did this over a couple of days, and they had all the different kinds of structures that would assemble. So the first one that you saw is self-similar, like all the parts make the same thing over and over and over again. The second one, the chair, it only makes the chair. It never makes anything else. Every part is unique though. So that's a big difference than this one versus the first one. Like every part has only one complementary pair. And we've done, then this one, it can make a bunch of different things, different kinds of lattices. This one was Velcro. The middle one and the first one were based on magnets. We've done surface tension. And the mechanism here is basically you need some kind of bonding. So you need like stickiness, Velcro, or magnets or surface tension, but it can't just be everything sticks to everything. It has to be error correction. So the error correction is either in the form of like geometric error correction, like in the chair, or in this case, if two parts bond, like on a Velcro connection, they might be off in this axis, or they might be off in like that axis. But then when 3 and then 4 connect, and the fourth one has to meet the first one, if it's not right, then it's going to be weak, and you're going to get a big long strand, and then it's going to break. And eventually you'll get one that connects, and then that one's going to be stronger than the previous one. And then when it connects to the next ones, it gets stronger and stronger. And so through that process, you can weed off the weak connections. So you need some kind of connection and error mechanism, and then you need energy. So in the flask, it was like shaking it hard or shaking it soft. If it's too soft, nothing happens. If it's too hard, everything breaks. So you need like just the right amount of energy. So we've done a lot of research over the years on that, and that led to this project in the Maldives called Growing Islands, where basically we got approached by this group to come to the Maldives, and it was a totally weird scenario. I'm telling you all these backstories. Hopefully it's interesting, but I was presenting at a sports conference on campus, and I was presenting our textiles work, and there was a woman in the audience from Sri Lanka who worked in textiles. And she came to the lab, we were talking about self-assembly, and then she said, my husband's Maldivian. Do you want to come to the Maldives? I saw this self-assembly stuff. Maybe we could do an underwater installation. Like that's how it started. And obviously I'm like, yes, let's go to the Maldives. That sounds cool. But then when we got there, it became like very clear islands self-assemble. Like islands are an amazing version of self-organizing systems. So we started studying these sandbars and trying to understand like how these self-organize. But it became clear that the real problem was sea level rise and erosion. You know, that everyone knows these low-lying islands are really vulnerable to climate change. And there's only two approaches that people try to use to solve this. One of them is building barriers, so walls, jetties, groins. The problem here is that it's almost never works. Like nature always wins. It always breaks it down, or it sometimes amplifies the negative effects. There's a lot of examples, the Army Corps of Engineers building these big permanent structures that then wash away homes afterwards. So this is not really a great solution. And the second one, which is even worse, is dredging. So almost any beach community, you'll probably see this. They do this in the Maldives. They do this in the Middle East. Lots of places do it. And they build an island in about a month. So they can build a new island from scratch with using dredging. But the real problem is that it destroys the reef. It's super energy intensive and the sand doesn't want to be there. So it's a temporary band-aid. It doesn't actually solve the problem. So we became interested in that the same amount of time that it took to build that artificial island, 3 sandbars built themselves. And these are massive amounts of sand. Like this is a boat. This is us, going up to one of these islands. It's over a meter above sea level and it shows up in a month. And so that was like the moment where we were just like, okay, that's the project. Like screw the art installation. Like the project is how do we promote the self-organization of sand? Because if we could understand that, then you could promote islands to grow naturally, or you could rebuild beaches and try to overcome erosion. So we started studying that. There's a lot of reasons people spend their whole lives trying to understand this. We don't have the answer by any means, but our hypothesis became it's the relationship between the ocean forces, so waves, currents, and tides, and the bathymetry. And if you have a specific bathymetry, then you'll get sand accumulation. Otherwise, you'll get erosion at certain times. Sometimes you'll see like a sunken ship will then change the beach, or you'll have a big reef, or you'll have a shelf. You'll have some kind of bathymetry change, and that causes erosion with certain storms or certain times a year. So our game became, well, what if we could change the bathymetry? What if we could then place something like strategically sink a ship, not literally, but like metaphorically, like what if we could place something that then would promote the sand accumulation? So we do computational models, so like physics-based models to try to understand if you have this geometry or another geometry, how does it influence the sand? We do lab experiments and we test like what happens if we place this object underwater and then we pump waves and then we study how the sand accumulates based on those geometries. Some of them we pump waves, some of them we have recirculating tanks, so we flow current over it. We can raise and lower the water to do tides, and we have these different geometric motifs, and you'll see a couple of those in a second. Another tank though we have is this one where we have 8 pumps and we turn on and off the pumps, and that's like changing the weather. So in the Maldives, they have 2 seasons, 2 monsoon seasons, and it switches like 180 degrees to one another half the year. So half the year, the water's flowing one direction, and the other half the year, everything's flowing the other direction. And so that's a really weird condition compared to like the East Coast or the West Coast, where we might have 45 to 90 degree swings. So in this one, we can change those monsoon seasons and we can see how the sand self-organizes. So imagine you're looking down from a satellite and you're seeing sandbars or islands emerge based on the flow of the water. So then we started to do machine learning and computer vision on this to try to like reverse it and say, well, what happens if we turned pump A, B, and C on? Or what happens if we wanted some shape to emerge? What kind of pattern would you need? So we have these 2 different scales of experiments, plus we have the computational models, and all of that basically just gives us intuition. Like almost nothing we do ever gives us an answer of what is actually going to happen because there's so many elements that are out of our control. There could be a tsunami that comes through. There could be like some massive amounts of big ships that come through that change the flow, or all these different things could happen. So really what we're trying to build is intuition. I'm thinking about these as like intuition machines, and all of that is for our field work. So we've done 9 now. This isn't totally updated, but we've done 9 different field experiments over the years in the Maldives. And these are meter scale structures. So this is a 2019 one where we did a 20 meter by 4 meter by 2 meter structure. And it's almost identical to the one that you saw with that black background. We were pumping waves and the sand was accumulating. It's just a much bigger version. And in 4 months, we saw this 0.5 meter of sand accumulation. So you can see on the left-hand side, the original state, and then the right-hand side, the light areas are where all the sand accumulated. But now we have 2 meters of sand. So the sand is all the way up to the top of the structure, and then there's about a 0.5 meter to go before the surface of the water. So this is really exciting for us because we placed the structure, we went away, and then came back, and there's now 2 meters of sand that wasn't there before. And that's just by changing the bathymetry, by placing an object in the right orientation with the right geometry. This is the most recent one we did in August. It's a 60-meter structure. All those things, those are little people swimming around, or like normal sized people, but look little, and they're swimming around. And the funny thing is all of those people are government officials, and they are from the Maldives government, the US ambassador, and US aid are funding this work, and they like wanted to go out there, and they're trying to be all official in their suits, and then they really just want to go scuba dive and snorkel around these things. But anyway, so we've done this one, and the big difference here is that it's omnidirectional. So the previous one, it would be like the one bladder on the right side. It would only work in half the year. So this one, the idea is that any time of year, it's always accumulating, and the goal is that it all accumulates in the middle there. We've done other ones. This one's a quickly deployable structure, and we could build 40 meters in an hour. So this one was like, what if you had low cost, easy to deploy modules? And so if you're a beach community or you have an island and you want to protect it, you could deploy these out, before a storm comes. You could deploy these out at the beginning of the season, and then all the sand would accumulate back on the beach. And then the other half of the year, you could deploy them to the other side. You could have like a fleet of low cost modules. But then we started to get into these like dense fields. The previous ones you saw are these more like ramp obstructions. But then we started to think about like mangroves or other dense fields. And we had this idea that what if we could float vegetation above the structure so that as the mangroves are growing down, the sand is accumulating up and they would meet one another. And the sand would then trap, or the mangroves would trap more sand and they would stabilize the sand. And then the sand would be accumulating from the bottom. So they would kind of work in harmony together. So we went out there and we made these like floating gardens. Each one of them had mangroves and screw pine and different native species on them. And we were hovering them above the structure. So here you can see some of the floating structures. And this is what it looks kind of underneath. This is on our structure. It starts growing all these different species on that. We've done many other ones. That's just a quick snapshot of what we're doing. And we have another one that we're supposed to go at the beginning of November. So in a couple of weeks. Another big component of this work, because of that tank that I was showing you that was like changing the weather, we started getting into satellite work, and we track a lot of these islands. We track the sandbars in the islands, and we started to realize that there's no tool to do this. Like we're doing it pretty manually. And if you had a beachfront property, or if you have an island, you have no idea how much sand you lost or gained. No one's out there monitoring it. There's no tool like air traffic control or the weather service that's telling you anything about your beach. So you have to physically measure it, or hire someone to do bathymetry surveys, or fly a drone and scan it, or do something like that. And you wouldn't really know what's happening. So that's one of the reasons it's hard to tell over a longer time span. Are we gaining or are we losing? So there's basically the convergence of more and more high resolution satellite image data and more machine learning tools. And so basically we're combining those two. And the idea is to create this like health monitoring system for the world. The big vision is that at any given day, every coastline around the world would be monitored. And we could tell historically what happened, but then you can infer from that and predict to say like next season, we predict this will happen, or, next month, this might happen. So we're slowly building that up based on that original tank. And then the last thing to talk about is you can tell we have something against concrete, because we're really always trying to get rid of concrete. We started trying to replace concrete with local materials. And there's this historic process in the US, it's called tabby concrete, or in Caribbean nations, they'll use this. A lot of like indigenous communities did something similar, where in this case, they take sand or shells or dead coral, you fire it at 1,000 Celsius, it turns it into lime, and then you add water and aggregate back in, and then you get concrete. So you don't have to import any concrete. So then you can print it, or you can cast it, or you can do whatever you want to do. You can add different aggregate in or different additives. And then we take those samples and we place them underwater in the Maldives, and we try to see what kind of marine life will grow, or what kind of coral, soft coral, hard coral, algae grows on them based on the different geometries, surface textures, material mixes. And the whole goal of this is that we could have local material. We could use that for building materials, obviously, but we could use it to build our structures. When we then place our structures underwater, they would both accumulate sand, but they would also promote coral growth, and the coral is what generates the sand. So the parrotfish come and chew the coral and then poop out the sand, and the sand would accumulate because there's more coral and because there's the structure. So you'd have this kind of like perfect circular process. We're still in the early days. We've shown that it's possible to make, but we don't yet know how to scale it. But anyway, we're excited about that process. All of the Maldives work now has been translated to another project in Iceland, and there's some other expanding locations, but all of this is about how do we build with nature? How do we take natural forces? In the Maldives, it's like ocean waves, currents, tides. In Iceland, it's volcanic, or it's erosion on the side of a mountain, or it's like freeze-thaw cycles from glaciers. So take natural processes and try to promote the accumulation or the construction of systems. So instead of thinking about natural forces as destructive, can we turn them and say they're constructive? And then we can work with them. We can sort of dance with these natural forces and promote natural accumulation or construction. So to wrap up, where I think all of this is going and sort of why we're interested in this, this is the classic motif for any industry. Architecture does this. I was just on a thesis committee, and the student was talking about how we are so interested in architecture about smart systems like smart thermostats and smart shades and smart HVAC and smart everything. But number one, all those things cost a lot more. Number two, they fail a lot more often. Like if you have a smart thermostat, you got to replace it like 10 times more than you'd have to ever replace a traditional one. Number two, they take a lot more energy. Number three, no one talks about the data and the data centers and the energy, power, water, all these things that it's used. So the smart thing becomes dumb and the dumb things become smart. And this happens everywhere. It happens in clothing, happens in shoes, like Nike made self-lacing shoes. So now we have to charge our shoes at night. And then there's like smart cars and there's like smart everything. And they just add more devices, more complexity, more components, more failure, more energy. And you're always up against that. Well, how do you make something smart? By adding less. And so that's what we were really interested in. It's like, is there a way to take things away from the process or to focus more on materials to make them smarter rather than devices? And I think there's two approaches. One of them is, it's not a vendetta against robotics. Like if robotics is not going away, probably there's going to be robots everywhere. We still should focus on smarter materials. Because materials, again, are what we're made out of. Materials are what the world is made out of. Materials have a lot of inherent capabilities. Materials love physics. Materials are great at physics. Robots are not great at physics. Computers are not great at physics. Humans are usually not that great at physics either. Materials are amazing at physics because they work with physics. They live in physics. Humans are great at creativity and collaboration. Robots are great at precision and repeatability. So if we work with those three, we have a really elegant system. But the more ambitious one, I was talking about that programmable matter grant that I was on, more than a decade ago. That is really interesting because at that time, everyone doing programmable matter was on robotics. If you look at all those researchers now, wherever they are in the world, almost none of them are working on robotics anymore. Most of them are working on soft matter. So most of them are in programmable materials, granular jamming, auxetics, biomaterials, 4D printing, you name it. It's all like, inflatable, soft robotics. It's all soft, squishy material things. It's not electromechanical. And I think that's an interesting shift. I mean, most of those are academics, but we're also seeing that in the robotics community, a lot more like soft robotics or things embedded in textiles, et cetera. So there's a shift. And that's because materials have the fundamental capabilities of robots. So they have information, sensing, and actuation. And if you have those three things, you don't necessarily need the electromechanical systems. So the vision of the lab is today we build smart robots and machines, and tomorrow we'll build smarter materials and environments. Thanks so much. Yeah. Yeah, sure. Yeah.
Totally in my own view about the art subtraction and using physical traits within math to simplify things and get intelligent behavior. That's exactly what we do. One of my favorite threads in your narrative, as you've shown the evolution of your work, was like how at the beginning, you might characterize it and some of the investigations as trying to impose geometric transformation from the and precision is important in that and be able to predict what that transformation is. And you really pioneered how to combine empirical methods, physical experimentation, but also computational simulation and that, but also working with mathematicians. Martin Evans just dropped a paper today on the mathematics of the Hohmann scissor.
Mm.
Like, and that's just like years of work to,
Mhm.
to get to that mathematical precision.
Yeah.
But Chuck Hohmann has been made a career out of just
Yeah.
just
Not this.
and exploring. That's what makes it, interesting, exciting. But then there's evolution from that to wanting to get that where some kind of geometric precision is important.
Yeah.
So then coming this like curator more of a natural immersion process.
Yeah.
That's a fundamental shift.
Yeah.
And so, I'm interested, at those beginning stages, how you saw the design process in mixing those three approaches. Maths, simulation, and experimentation.
Yeah.
And then what's the mix now?
Yeah. Yeah, great question. I think of it as a spectrum where on the one hand, it's like top-down design with bottom-up assembly. Like I want something to happen. I want a chair to emerge, but I want it to build itself. Like that's that. The other end of the spectrum is maybe the farthest end is just like chaos, like anything can happen. Just let something go. And that would be not really a garden, but like an out of control garden or something, right? Then there's a garden, which is like a curated, or that's like Olmsted landscape, like curated out of control. And maybe the Maldives is closer to that. Like we will intervene, but we want to dance. You do something, I do something. And that's maybe more like the garden. Like I plant the seeds, but I don't have control over everything. But I could trim the weeds out, or I could do this, or I could do that. I think I like that's more than the other side, because I am interested in the design possibilities of that. I'm interested in like not having control over the design output all the time, but truly finding a way to collaborate, like where amazing things emerges. Like in the Maldives one, it starts creating these V shapes, which we never predicted it to have, these sand patterns that emerge. Or those sand patterns in the tank that started emerging. Like I never would have drawn that. I never would have guessed that would have happened. And I'm excited about that. Like design emerges through systems. But the early work was always about like demonstrating that something surprising could happen. And oftentimes in order for it to be surprising, you need to be recognizable. Like the chair emerging is like, what? Like why does that happen? But if something weird assembled, then you'd be like, okay, is that supposed to work or not? Like, did that do anything? So that's why we, in the beginning, or like the letters MIT, or like the 50-foot protein was cool, but it was like, no one knows what a protein looks like. So it's like, is that a hairball? Like, what is that thing? So that a lot of times in the beginning, it was like, let's do something that is recognizable and would be surprising. And like, I'm always interested in the element of surprise as a designer, and like, especially when we do exhibitions or if we have public work, like, can we show stuff that someone would be like confused, surprised, inspired by, that's different? And that sometimes is the most boring design version of it. But it's also hard because you don't want it to just be a total mess, and you don't want it to just be like totally out of control. And then there's a fine line of like, how much control do you have? And if you start having too much control, then you're back at the same part. Then you might as well just sculpted the island, So it's hard, but I'm more interested in like design wise, the freedom of it. And then in terms of like simulation and iteration, like we're definitely not a simulation lab. There's people that are way better at simulating almost everything I'm shown here than we are. So that's not like our main output. We do a lot of simulation work, but yeah, I guess I'm a little bit skeptical of simulation. In like most of our things that we work on are like either truly complex systems or like complicated, and simulation tends to not be very good at that. Even simple ones like textiles. We had a grant and there was a group with us on that grant. I won't say who it is, but they got kicked off the grant because their whole thing was about simulation and they just couldn't do it. Like simulating textiles is really, really hard. And there's a lot of, the best someone can do is like how this thing meets that thing in like a 10 by 10 grid or something, right? Like you have a sweater and I pull on the front of the sweater, how much force is felt on the back of the sweater? Like no one knows how to simulate that, but we know how to make textiles. And so Maldives is the same. There's like, how does a grain of sand move with water? Or there'll be like coastal, zoom all the way out and look at how a coastline moves, but there's like nothing in between, and those two things don't talk to each other. And like, So there's so many things that you can't simulate. And a lot of times, like on the 4D printing work, we spent a year with Autodesk and another group, and we built the simulation tool and we published a paper on it. And then like the next year we started working on carbon fiber and nothing worked anymore. And it's like, all right, that was a waste of time. Now I need to build another one. And so I'm like, I've over the years just gotten less and less confident that simulation is that valuable, other than building an intuition, like generally what seems like it's working. But it's almost never possible to actually simulate. And yeah, I guess I've started to think that the thing I am optimistic about though is a new version where we're just watching things, and through that, like through machine learning tools and computer vision stuff, you just watch it and then it doesn't understand why, but it's very good at telling you what will happen. I think that's more interesting. Let's build lots of iterations. Let's be empiric. Let's try, get our hands dirty, mess, play, start watching it, and then have a tool that understands it maybe even better than we do, because it can see many more things at the same time and make inference between it. Yeah.
You're working in a few inherently risky environments, space, island nations.
Yeah.
And not simulating it.
Yeah.
How do you?
That's risky. Yeah, it's risky. And I guess I'm very skeptical of the people that do simulate it and say they know what's going to happen. Like in the Maldives, there's all these consultants. I mean, this is a much longer story, but there's all these environmental consultants that basically have a monopoly over it, and any new project needs to hire them. And then they come back with these packages that like predict what's going to happen. It never happens. They're always wrong. Something else happened. And then they're like, oh, yeah. Well, it's because you need to pay us now to like fix that thing that just happened that we didn't predict. And we'll predict something else that doesn't actually happen. Like they like have so much confidence in their models that are totally not right. But I mean, they're doing the best they can. They're not like trying to lie, but they just don't know. And then they have to make a business over pretending that they know. And then they have a contract that says like, none of this is guaranteed, or they'll say like, hire us again when it doesn't work. You know, like, so I guess I've gotten like very skeptical of those, and they'll tell us all the time that they like know better than we do about what's going to happen. It's like, maybe, I mean, yeah, you might be smarter than us. I don't know. Like, we don't know what's going to happen either, but we're interested in seeing what happens. And they're not using satellite images, and they're not using the machine learning tools. They're using like physics-based models that are very, very narrow. The best thing that they have that we don't have is a whole lifetime or many generations of knowledge, local knowledge. So I do totally believe that. And they have told us things that like just were very hard to believe and then turned out to be true, which is really fascinating. And it's just because like I saw that with my eyes, like I saw this happen. I know that it happens. And so those things I think are really interesting, but that's also hard to capture too. Like it's just people seeing things over a long period of time. So we just try to collaborate as much as we can with, locals and people who are experts. And I'm being a little bit like dismissive of that. Like I love it when we have amazing engineers that are analyzing everything and simulating it. And it's not like I'm just like, ignore that. It's more like, okay, that's valuable. Probably doesn't tell the whole story. Let's simulate it with a tank and do physical. Let's do field studies and let's combine all of those. Maybe we can help your model get smarter. Maybe we can help this one get smarter. And so I just think of them as like individual pieces into a larger puzzle. And I guess I'm more just like humbled that we won't know for sure. And we have to try things, and we have to just build intuition. Otherwise we could do nothing, but we need to try something. And so you just have to like mitigate the risk as much as possible. Do all the simulations you can, do all the tank experiments, do all the field experiments. You'll probably still be wrong. So if you're wrong, what we are always trying to do is that we can pull it. Like anything we put in the water or anything, like just pull it if it's not working, or change it, move it, adjust it. Like nothing is permanent. Everything could be adapting. And that's kind of the best we can do. So that's like that kind of risk. There's also other kinds of risks, like lots of people are spending lots of money, and there's big groups and organizations relying on us to do this stuff. And there's those kind of risks too. The space stuff isn't that risky because we didn't send anything to space in that case. Like we just made a prototype of a spacesuit. It would be a lot more risky if we put an astronaut in the spacesuit, and I'm not sure they would let us do that. I don't know. Other ones, there was one here.
Thank you so much for that presentation. I don't think of that, amazing. And I love how, I think one of my favorite parts was how throughout each of the projects, there was such a focus on reuse and recycling. And how it was such a great goal of the instant concrete, or the concrete of compaction idea, and the instant metal. And I guess it was inspiring because it remembers what culture kind of forgets sometimes, which is that we live on a finite earth, and that the goals and dreams that were possible maybe 50 years ago is not anymore because of how much we are mining the earth. So I guess my question is, I absolutely love the shifting focus from smartness being, whatever it can do and for as long as it lasts, and rather the process of using less materials and making the process much more efficient. It seems like some of these materials maybe require a little bit more human manipulation, and like the pH, like the material that changes structure based on the pH of the water, and it seems, I don't know, maybe to me a little more contrived than what you would get from running the machine.
Yeah.
So does that process of making these smarter materials incur, does it end up incurring more waste? Does it end up being counter eco-friendly? Does it create problems or issues there?
Yeah, I see what you mean. Interesting. I hadn't thought about it like that before, but I guess it gets back to what I was talking about before, the spectrum of like totally in control to totally out of control, because almost every material is active in some way, with some kind of, well, literally every material is active in some way. It just depends on what scale you're looking at or what kind of activation energy. Some are more like active at a macro scale, but most things are seen as a nuisance. And we try to stop them from being active. Like often in textiles, it's like, you don't want something to felt unexpectedly, or you don't want something to shrink in the washer and dryer, or in wood, like you don't want your deck to curl or your like cabinet veneer to move or something, like most materials are active and we try to stop them from being active. And I guess I feel like what we're trying to do is amplify the active behavior and curate what's going to happen. And through design, like design of the textile knit structures, or design of like the printed material, or design of, I don't know, how something comes together, we're going to curate what behaviors it's going to have. But we're not adding some new material, there's no like magic material we're using. All of these are like standard materials. It's just that the relationship between two material properties, or the relationship with the environment, causes some change in behavior. And if we can understand that, we can play a design game and say like, this one will be here, this one will be here, and then it'll do that. It'll like have some behavior. So there's no reason that it would inherently be less environmentally friendly, or cause more waste, or even cost more, because the materials that we're using are the same materials that anyone else would use. It's just that we put them in a specific configuration to promote some behavior to have. So yeah, oftentimes people are surprised by that. Like what we did is not any more expensive than the static thing, or the out of control thing, because it's using the same materials. We're using typically the same processes, just like thinking more carefully about the relationship between materials and their environment. Yeah, so I don't think there's any reason that it should be worse for the environment, or be more, wasteful, etc. I will say that a lot of our work now is shifting towards more like mono materials, especially in the textile space. And that's for like recyclability, because the easiest motif is take two materials, have different coefficients of thermal expansion, and then they start to move, or like swelling rates with moisture or something else. But when you have two materials or more in systems, they often become hard to disassemble. So then it makes it harder to recycle. So one of the big challenges in like the project with Emiko that I was talking about, like that is all mono material. And the big challenge was like, how do you get it to bulk and expand with only one material? And so that has been a shift in our work. It's a little too easy to just like throw two materials at something. And that can be, that isn't great for recyclability, but everything what everyone is wearing here today is not mono material. So It's not worse than state of the art, but it's not great. So we are moving towards monomaterial, and then it can be recycled. And then there's a whole nother layer, which could be, let's not use synthetics and let's do monomaterial or fully natural. And that's a whole nother space. Yeah. There's one over here.
Hey, thank you for the lecture. I have a similar question kind of related to material and waste. Looking at, you mentioned like the mangroves and the coral, talking about the islands. Are those do the islands you're creating last long enough to sort of adjust the ecosystem around it? And are the mangroves and the corals kind of gonna be brought in as stabilizing factors, or are they thought of more like a consequence of what could happen with this project?
Great question. Well, I will say first, we haven't built an island yet, so we're still growing, we're still going. We've accumulated a lot of sand, but our goal is to breach the surface of the water and like, have a sandbar. But that is also a development project. Like realistically, the reason to grow an island is to make sustainable development. Because any new island, any development project is using dredging, and it destroys the reef and it's super nasty. So really we're trying to tackle dredging and say like, stop dredging. There's a natural way to have development. But there's also a question of why do we need development? And there's a whole debate right now in the Maldives. They have like 1,200 islands and they're still making new ones. And there's only like 200 inhabited. Like, why do you need to make new islands? There's a whole nother question about that, but I'm not going to get into that. So the island is more just like a blank canvas experiment for us. Like we take a reef flat, 2 meters deep. Can we grow a sandbar that wasn't ever there before? And that would be like a really great proof of concept for us that this would be possible. But the more near-term one is the beach restoration. So that's like really much more urgent and more pressing. And we've done one before, and now we're doing another one coming up that's just focused on the beach. And then when we got into the mangroves I thought were interesting because it was about trapping sand and stabilizing sand. So that is a kind of interesting tool to use like in the beginning of the process and the end of the process. The coral, we sort of stumbled into that because everything we put underwater just started growing stuff like algae and soft coral, and then any of the metal structures we put underwater just growing like football sized coral on them in a year or two. So we were like, this is interesting. Like we didn't know anything about coral, and we weren't like trying to grow coral, but then started thinking about, well, maybe our structures could grow coral. So the new beach one, this is the first time that it's first of all going to be around people. So it's like right off of a beach, so people will be there. So we had to design it so that it's also like a positive experience. Like they would go there, and like when I was showing those people swimming, the next one, like it's going to be a destination that they can swim and scuba dive and snorkel around, but it would try to promote coral growth. There's also a whole other interesting anecdote that like anything we put underwater, just like thousands of fish flock to, because there's like nothing in this reef flat. It's just 2 meters deep for as far as you can see, sandy bottom. So there's no like safe spot for the fish. But when we place stuff there, especially when it has all these like nooks and crannies and shadows, they just like all come there and just create homes and habitats and stuff grows. So that's been like an interesting byproduct that we weren't originally designing for, that now we're trying to design for. There's a whole nother part to your question about like how long-term versus near-term, like permanent, temporary are these. Some of them, like the ones where we placed it with the excavator, those were temporary, like we could take them out, move them. Some of them are more like semi-permanent, where we want to place our structures and we want to accumulate sand. Maybe the sand starts to engulf the structure, so it's always under there as like the foundation or stabilizing force. And we're looking at all of the above. Like maybe the coral starts taking over and then disintegrates our structure and it becomes a reef over time. Like I think we're interested in all of those. There's not like a single solution, because certain ones you want temporary and other ones you want longer. But the growth of the mangroves and coral and all that has just sort of serendipitously become part of the project. And I think it's good. We want to create like positive, healthy ecosystems, have a positive impact, but it wasn't where we started.
I'm curious about with the reversible kind of building practices you've been experimenting with, if there's been if your work's touched ways to like figure out structural rating for them, given that like if they're gonna be applied to like real structures, like they can customize to whatever use they're gonna have and ultimately want to be disassembled easily. So how do you like figure out how to predict that without just testing to failure with each use?
Yeah, interesting. So I will also say, like, most buildings you don't want to disintegrate. So like jamming is not the best if you want to make a permanent building. You don't want someone to come up and be able to like wind your building down. So it's not particularly useful for everything. It's interesting for like weird research academics that are like, what if we made reversible concrete? I didn't show one, but we did a project where we made like switchable jamming. So we jammed a structure, we had a top and bottom plate. And when you compress it, it gets stronger with load. So when you compress it, it jams. When it's not compressed, it just disintegrates. You can like push it over. But if you compress it, then you can move it, and it's like a module. So we made like a column, and you can turn it into a bridge or beam, and you made a wall and turn it into a slab and walk across it. And so that way it's like, if you want to remove it, you take away the load, it disintegrates. But if you don't want to remove it, as long as you compress it, then it's really strong. So that's a way to like turn it on and off. And then loading, yeah, we have a DARPA project right now that's all about this. It's for runway repair. And that's an interesting one because it's not freestanding, so it's a lot easier. It's in the ground. Could be for foundations or other things like that. And it's very fast. Normally they'll pour concrete and asphalt and stuff, so then they have to wait 30 days or however long for it to cure. This case, they can find local materials, they could jam it, and then they could take off pretty quickly. So that's a great one. It doesn't just like fall over or disintegrate. It's in the ground. That one is mostly about the minimizing deflection. There's a whole nother, like, related to the simulation conversation. There's all these physicists that were at that conference that study jamming, but they study spheres and like very simple geometry and how they jam. And it's really hard to jam rocks of arbitrary shapes. That's hard to simulate. There's a little bit of work in that space, but mostly we do it empirically. Like, we build tons of columns, we load test them, and like we're loading them so much that the rocks are turning to dust. So we just like keep loading them until the whole thing literally disintegrates because of load, not because of like falling apart. And you know, there's a bunch of techniques we've developed, like what's the fiber to rock ratio, what's the layer height. One of the big factors though is like, what's the tensile strength of your fiber and what's the compression strength of your rocks, and that will definitely, you know, make a much stronger structure. They're really good at static load. They're really good at impact. They're not so great at abrasion or vibration. Those are like the two, unless they're constantly under load, then they're fine with vibration. The other interesting thing is that they go to a semi-solid state when they fail. So like, even if we made like a 14:1 column aspect ratio, and it's super thin and slender, and if you just like hit it, it buckles, but then it catches, and then it keeps jamming, and then you can hit it again, and then it like buckles and keeps jamming. So it keeps going. And you can also sculpt it, which is really weird. You can like move it, push it, and then it jams again. So there's some cool things about it that normal concrete wouldn't do. But in general, I don't think it's going to replace all of our concrete anytime soon, because yeah, the reversibility isn't totally ideal. It depends on the application. Yeah. Okay.
Hi, so I really enjoy listening to how you talked about like how you are trying to lean away from like predictability and more towards like intuition when it comes to simulations. And I feel like in part as people we have become really comfortable with like predictability, or like the illusion of predictability, because with all these like so-called smart items appearing in the market like every other day. How confident are you on people being able to embrace like the curated chaos of these materials? Because like we've just become like obviously very like comfortable with whatever predictability that the market is currently feeding us.
Yeah, great question. I'm thinking about this stuff a lot, and it, you know, relates to Jay's question about like simulation and the risk in certain environments. I mean, we're seeing like SpaceX launch these things and then sometimes blow up, and sometimes they catch the rocket, and sometimes they land the rocket, and all it's like very risky, expensive things that they have amazing engineers simulating till they're blue in the face, and sometimes still get away wrong. And we see that all over the place. I guess the best I think we can do is simulate as much as possible, test as much as possible, and fail as much as possible and learn through that. And then eventually you'll get better. But I don't believe that we can always predict every single aspect ever. And I think we do get caught in that trap. Like we think that we have really smart engineers and we have really amazing simulation tools and we can just know every possible scenario, but I just don't believe that as of yet. And from designers, like it's a weird thing because coming from a design world, like intuition and like trial and error and failure and prototype and play and experimentation and empiric testing is natural. Like that's what we do. But then when you go, like most of MIT is not that way. And we talk to like academics and science and engineers, they're like, what are you talking about intuition? You know, like we don't want to talk about intuition. We want to know like what is your thing going to do when it goes to when you put it in the water or whatever. So they don't like that. But I think it's just like ignoring all of these other things. And I feel like that in a way is like part of the magic sauce, that like we're embracing that. And through that, we can have these weird ideas and achieve these weird things by not being embarrassed and say like, I don't know about granular jamming. I'm just going to try stuff and I'm going to find something that jams. Where the simulation person would like try to simulate this and never achieve this thing, you know. So I feel like that has been like a big part of our lab, that we're just like not afraid to have a million tries at it and fail a million times and use all the best knowledge to have some intuition and take a risk and try something big. But does the general public appreciate that? I don't know. I've had like a love-hate relationship with failure for a long time because of this, because in a lab and as designers, we all have failure all the time and it's fine. But the general public doesn't like failure. Like you can't show up to MoMA with an exhibition and then have it fail. Like they don't care about failure. You know what I mean? Or like you can't have this big public project that then fails. Like people aren't happy when things fail. So that's like I mean, I get it. I don't want things to fail either, but like that's, you know, we all know that we're pushing the boundaries here and there's no way to totally know every possible thing. So that's a frustration in a way. But the thing that's also frustrating is that all of us deal with chaos every single day. Like we can't predict the weather very well. And we understand that it may or may not rain, you know, or like a garden or traffic, or, you know, there's so many things, like almost everything in the world is not predictable. But we pretend that it is predictable, or we just go with it and we go with the flow and we adjust and we're all fine. Like we can't predict if there's going to be a thunderstorm right now, this moment as we walk out or not, but we're okay. It's all right. We don't have total control over everything. But when we get to manufacturing or construction or many of these spaces, there's a perceived control and no level of chaos is accepted, right? And like we want control over step by step by step. But like in certain industries, like brewing beer or wine or cheese or gardening, or like some of these are manufactured systems where like you don't have control over so many processes. And that's why we get like amazing wine from some region, but like we couldn't have chemically done that probably. And it's just that like we were able to give up a little bit of control, but gain all of these other benefits. So it is interesting, but most people don't think about it like that. And most people want more and more and more control. But you realize that if sometimes you give up control, things happen that you couldn't have ever done yourself. So I think there is a shift that needs to happen. I think we're going in the wrong direction. We're going more towards control and simulation and knowing everything and whatever. But the out of control is good. I mean, the out of control sometimes leads to much better outputs. Yeah. There's one more.
I really appreciated seeing your approach to process through material and experimentation. I think that a lot of the ways that we approach problems, at least like this MR program, is through drawing to solve problems. I'm wondering for you in your career, maybe when that approach to experimentation and material started to develop, if that was something that was always part of your process, or if that actually started to happen maybe more in the research.
Yeah. Well, even before like architecture school, I was really into photography. I had an aunt and uncle that were like professional painters and freelance artists, and was interested in art and drawing and making, and I was like made stuff in the garage. Like I was like a creative maker designer type person. And then went to architecture school in Philly, and it was pretty conventional. Like we didn't have any digital fabrication tools. We learned by hand drafting. Like it was pretty conventional. And then there was like this one oddball professor that happened to be one of the early people at Zaha's office. And like, that's how I ended up going to Zaha's office. It was just like total randomness, this one professor. And that kind of like changed my perspective and changed my world. And like that being there, then I started getting interested in computation and how software tools would change the way we could design. And I started teaching myself how to write code and got into that. Yeah, we had like zero digital fabrication tools at the undergrad school that I went to. But another weird thing happened that one of my classmates, who's now the co-director of Lab, Jared Laux, his father had a sign shop and he had a CNC machine at home, like totally random. And so then we would just go there on the weekends and fabricate stuff. And so then it kind of, the pieces started coming together. Like I was writing code and generating things. We had a machine, we could digitally fabricate things. We were starting to build installations around the world. So that's kind of like how it started getting into that space. And at that time, then I realized I was very interested in computing, and I made a decision that I wanted to go to MIT to study computing from computer scientists. And that's like why I wanted to go that route, because I felt like I had a strong architecture background and I had a strong design background, but I didn't know this other world, and I wanted to learn that other world and bring it back. And so that's kind of how I got into it, and then got into the research and more materials and experimentation. But through MIT, I got less and less interested in computing, which is weird because I got a degree in computer science. But like in the middle of it, I was just like, I hate this. This is like, it totally killed my love of computing. And same with machines and fabrication and robotics. It was like, by the end of it, it was like, I don't want anything to do with any of that stuff. You know, I want to focus on materials. So it went a whole nother direction. The computing part is just because computer science classes at MIT are like the exact opposite of everything I wanted to do. It was like, how optimal is your algorithm? And I'm like, I don't care. I want, how many mistakes does my algorithm make that lead to surprising results that are amazing and something I could have never dreamed of. I don't care how optimal it is. I don't care, like, yeah, whatever efficiency my algorithm has. But so I was like a very bad computer science person and just wasn't interested in writing software, but I was more interested in like design output. And so, yeah, I got more into materials and focused on that whole thing, and then got the opportunity to stay as faculty and experiment. I don't know that there's like a straight path. It was more just like searching and following what I was fascinated in at the time, and had great opportunities to explore it, and then kept going and kept searching. And then, you know, the story that I'm telling is something that emerges. It's not like I started out having this story and having this goal. You like think through projects and you're like, what are we working on? What do we care about? What are we interested in? You're like constantly thinking about that, and then framing these narratives and like challenging yourself to do better in certain aspects, and like pushing forward, and the story kind of emerges. I don't know if there's any lessons to be taken from that other than keep playing, maybe.
Actually, I think that's a beautiful place to end the talk, the word play or play. But it also makes me think that you talked quite a little bit about, you even used the expression like the secret sauce, etc. I think that's one of the things that just architects to work for, that we feel kind of comfortable with, this idea of kind of the unknown, and that engineers are about to kind of often have a goal and try to prove it, and then be able to describe that process such that it can be repeated.
Yeah.
And that in architecture, there's always that, even if I do that line, what happens?
Yeah, let's push it a little bit.
Sure. It's like, right, so I wanted to say that it's interesting because while this is not the language that the Institute uses, when I arrived at MIT, I felt, oh my God, these people are not aware, but everybody's designing something. And I think in that sense, like, again, our capacity to understand that we can take on those processes and turn them into design exercise is what I think makes a good environment for sort of creating like the type of, I think, incredible impact that you have had in the Institute in terms of bringing together different areas of expertise, very actually precise sort of knowledge bases to produce different outcomes. I know we have to hear, but I just wanted to say something about scale, because for so long the work was, in the beaker.
Shaking
and the
flask.
tank, and the question of how it scales up and at which point we go from objects to architectures and from architectures to environments.
Yeah.
And I mean, the INAP project is
Mm.
sort of amazing, and it also brings in the dimension of time. We can rush those processes in the lab, and nature does its own thing.
Yeah.
And we're just such a small part of the temporality. So I think, 10,000 other questions that we could ask about the work, whether it refers to the production of architecture or that sort of temporality of the kind of the larger world in which architecture sits,
Yeah.
and that subjected to those forces as a feedback mechanism to what we. Thank you.
Yeah. Yeah. Pleasure. Thank you.